So we wanted to prove the weak version of PCP theorem. It says that NP is contained inside PCP poly n, comma 1. Okay. In order to do this, we were using Walsh-Hadamard code words. Okay. So we are looking at the problem of quad EQ. Therein we are given a family of quadratic equations. Okay, so we have m equations and the number of variables is n. Okay, and these equations are over GF2, which means all the operations that you are doing are modulo 2 operations. Now, we said that we can think of this as solving a system of equations A u is equal to B, where A is a matrix. It's an m cross n square matrix, and U is an n square cross 1 matrix, and B is an m cross 1 matrix. Okay. So we want to solve this equation such that the matrix U is equal to the tensor product of some n cross 1 matrix or n cross 1 vector. Okay. So quad EQ is NP complete. So if we can somehow produce a certificate to show that AU equals B and U is a tensor product of small u with itself, then we can say that if we can produce a PCP certificate which says this, then we can show that NP is contained inside PCP with these particular parameters. Okay. So one certificate for quad EQ would be the assignment of the variables. Okay. But if you look at the assignment of variables, what variable takes what value, that will be too long a check. So you'll have to query all the bits of the proof. Instead, we will expand this assignment into a large word or a large string, such that by following a certain protocol on the string, we can be assured with reasonable accuracy that AU is equal to B and U being equal to U, tensor U has a solution. Okay. So the proof in PCP, the verifier will have access to a proof, and that proof we will think of as pi, which is a string or a binary string of length 2 raised to n plus 2 raised to n square. Okay, so this long string, we will think of it as having one part of length 2 raised to n and the other part will be of length 2 raised to n square. And we will assume that the first part is a linear function f and the second part is a linear function g. In other words, these linear functions are essentially nothing but the Hadamard codes or Hadamard encodings of certain other strings. Okay. So here n is a number of variables. Okay. So the function f, we will see it as the Walsh-Hadamard encoding of u, where u is the satisfying assignment. For the quadratic system, AU equals B and U equals U cross U. So if there was a satisfying assignment, then the Walsh-Hadamard encoding of that is the first part, and the second part we will see as the Walsh-Hadamard encoding of U tensor U. Okay. So U tensor U is going to be thought of as a matrix which has been converted into a single string. Okay. So if U is a vector, is an n cross 1 matrix, then U tensor U will essentially be a matrix, n cross n matrix, whose ijth entry will essentially be ui dot uj. Okay. And this matrix, if you think of it as a single vector of size n square by some canonical encoding, you can think of that single vector as the second part of the proof. Okay, so take the matrix of size n square cross n square, and then we will append row after row, and what you get there is the string G. Okay. So string G, you can think of it as you tell any position in the U cross U matrix, in the U tensor U matrix, that can be queried, okay, by means of the function G. U cross U is a n square sized vector. The Walsh-Hadamard encoding of that vector will be what is G. Okay. So that's the way the proof string is going to be. Now, once this proof string has been given, the verifier is going to query some part of the proof string. Okay. And if this is indeed the correct proof string, in the sense it was the encoding of a satisfying assignment, then your verifier or the protocol will say that it is in fact a satisfying instance. And if it is not a satisfying instance, will show that whatever be the proof that is being supplied, with high probability the proof will be rejected. Okay, so our aim is as follows. Show that pi equals, let's think of it as f followed by g, will be accepted with probability 1 by the protocol if f and g, where the Walsh-Hadamard encoding of U and U tensor U, and U is a satisfying assignment. And the second part is if any formula or quad formula or quad EQ system if any quad EQ instance is unsatisfiable, in other words, if every possible U is a bad, I mean, if you look at any possible U, all those will give rise to incorrect proof strings. Okay, so those are precisely the bad instances or the unsatisfiable instances. So these unsatisfiable instances will result in the proof being rejected. So if any quad EQ instance is unsatisfiable, then the proof will be rejected with high probability. Okay. And the number of queries made is some constant, and randomness used should be order of poly n. Okay. This is what we need to show. We have to design a protocol which satisfies these three requirements. Okay. So we will give the overall high-level view of the protocol. The protocol basically checks three things. The first thing that the protocol checks is that f and g are linear. Okay, so we are given a string of length 2 power n plus 2 power n square. If you look at the first 2 power n bits of the proof, that is what we call as ref, and this next 2 power n square bits is what we call as g. We will verify that these two are linear. That's the first part. Okay, so in other words, we're checking that these are, let us say, Walsh-Hadamard encoding of some string. We argued earlier that checking whether it is a Walsh-Hadamard encoding is very difficult. It will require too much time, and therefore, instead of linear, we'll be satisfied if we can verify that they are almost linear. Okay. If they are not almost linear, then our algorithm will quickly find out that they are not almost linear. Okay. The first verification is that they are almost linear, and then we will check if G encodes U tensor U, where U is the string encoded by F. And the third part we will check is U is a satisfying assignment for quad EQ. Okay, these are the three things that our protocol will check, and we will verify that the number of queries made by this protocol is constant and the randomness used is O poly n. Okay. Now, if you want to look at one random location inside this string, okay, each location can be, so you can think of this to be, let us say, less than 2 into 2 power n square, and each location, if you want to access, each location has an address of size, let's say n square plus 1. Okay. The address of any location is surely less than n square plus 1, because look at all bit strings of length n square plus 1, that's going to be greater than 2 into 2 raised to n square. So each address is going to be of length n square plus 1. So if you are querying only constantly many locations, then each of those addresses some poly n, and therefore if you're querying random locations, you're querying just constantly many random locations, the total amount of randomness would be limited. Okay, the number of randomness used would be limited to the extent of O poly n. So that we'll just ensure that the query is made as constant number of queries. So, and if these tests are passed, that is, if f and g are linear and then g encodes u cross u and u is a satisfying assignment, then it means that the formula is satisfiable. If any of these tests fail, then we will declare the formula as unsatisfiable. And for all the satisfying instances, these tests will be satisfied. For all the unsatisfiable instances, these tests, at least one of these tests, would fail with high probability. That's what we will show. Now, how do you check if f and g are linear? We need to check only if they are almost linear. Okay. Because of the properties of Walsh-Hadamard encoding, we could just check at a few locations. Okay. So if we wanted, let us say, an accuracy of 99.9%, okay, we can look at a 1 minus 0.001 linearity test. This would require C by delta queries. Okay, so the C and delta, it really does not depend upon the input size. Okay, this is of our choose the 001 or the delta is our choice. So depending upon the accuracy that you want, you can decide how many times you'll have to run the linearity test. Okay, so you can run the linearity test, and once you have done the linearity test, f and g, you can, on both these parts, the first 2n bits and the next 2 raised to n square bits, if you run the linearity test, And if the functions were actually linear, then of course the linearity test would say that they are linear. They are not actually linear if f or g is not 1 minus delta close to a linear function. Then the property of linearity test states that would be detected with high probability. Okay, the proof would essentially be rejected with high probability. Okay. And if the instance was in fact satisfiable, you can just give the correct satisfying assignment u or its encoding. Okay, so satisfying instance, you can give wh of u and wh of u tensor u. Okay, if these were concatenated and presented, then the test would surely be a success. But if they were not even 1 minus delta close to a linear function, the linearity test will detect it with very high probability. Okay. So now what we have is we can assume that our bit string that is supplied to us has two parts, and the first part is very close to a linear function. The second part is also very close to a linear function. Okay. So if you assume that the adversary is trying to cheat us, he has to surely give us some functions which is very near to a linear function and some other function which is very near to a linear function. And there is precisely one linear function which is very near to any almost linear function. There is precisely one linear function which is very close to a arbitrary function. Okay, so f is not, suppose f was not a linear function, then in the vicinity of f, the neighborhood of f, there is only one function which is linear. Okay, nearby means they agree on many bits. Okay, so that function, let's call it as f cap, and let this be g cap. So if the adversary is trying to cheat us, he has to give some function which is not linear, but even from that not linear function, we can infer a function f hat and g hat, which has to be linear. Okay, so if our test said that these functions are linear, we know that they are encoding the function f cap and g cap. Okay, so for the next test, this is the first test. The next test, we can assume that f cap and g cap is what we have f hat and g hat were what were supplied to us. If we want to locate the value of f hat at one particular location, we can do the local decoding. So f hat and g hat can be computed at any arbitrary location. Okay. F hat is a function from 0, 1 to the power n to 0, 1. Okay. And this function can be, you can compute the value of this function at any point with high probability. You can compute it correctly with high probability because of local decoding. Okay, wherein if you had to find the value at x, you find the value at x prime and x plus x prime. Okay. Add the values, you will get the value at x. Okay, so that's called as local decoding. So f hat and for g hat, that's going to be a function from 0, 1 to the n square to 0, 1. Sorry, 0, 1 to the 2 raised to n. Okay, so this is 0, 1 to 2 raised to n. This is f hat is a function from 0, 1 to sorry, f hat is a function from 0, 1 to the 2 raised to n to 0, 1. It's a string of length 2 raised to n. And g hat is a function from 2 raised to n square to 0, 1. Okay. Now we need to verify that g actually encodes u cross u, where u is the string that the second check is basically check that g hat encodes u cross u or u tensor u, where u is the string encoded by f hat. Okay. So what we have to do for that is query f at, it's two locations, at r and r prime. Okay, so we can compute fr and fr prime. Okay, and this should be equal to g of r tensor r prime. Okay, so this is the check that we will perform. So if this check fails, if this is equal, then we will say that this test is passed. Otherwise, we will say that this test is failed. If we want a certain accuracy, we can run it multiple times. Okay, but let's look at one test. And if the function f and g were of this kind, okay, so if let's say quad eq is satisfiable, then there is a u, okay, that u can be given by the prover. Okay, the proof string is basically produced by means of u. Okay, and if you look at fr and fr prime, what are these? Okay, fr is nothing but u product with r. Okay, it's an encoding of the string u, and at location r, that's just u dot new product with r. This product was defined as ui ri summed over I varying from 1 to n and computed mod 2. Okay, and fr prime is going to be u product r prime, and that's going to be summation I going from 1 to n ui r I prime mod 2. Take the product of this, the product would be, okay, so we were doing this for fr, so basically querying the proof string and looking at location r. Okay, but we know that this is going to be an almost linear function, and the actual function was f hat. So if you think of the function f hat, okay, this must be equal to summation ui ri summation uj rj prime, and this, by rearranging, you can see that this is equal to double summation over I comma j ui uj ri rj prime, and this is nothing but, if you look at the tensor product of u with itself, that's going to be a string of length n square. And if you take the tensor product of r with, so this is u tensor u, and if you take r tensor r prime, you'll get another string of length n square, and this value is going to be just the product of them. Okay, so that is the, so this product is just, so u tensor u multiplied with r tensor r prime, and that is just nothing but in the string g, whatever is at the r tensor r prime position. Okay, r tensor r prime is some particular location, because g is a string of length 2 raised to n square, and each position is indexed by two vectors r and r prime. Once you vary it over all positions, you will get the entire string. So this value is nothing but G R tensor R prime. So if the string, so what this shows is if the string supplied by the prover or the proof string is actually a linear function f cap, then this test would automatically be satisfied. Now, if it was not a linear function which had these properties, okay, if G didn't encode U tensor, what will happen? Okay, so we'll look at that particular case. We can assume that f is linear. Okay, we know that it is almost linear, and therefore there is a unique f hat, and that f hat can be inferred from this function. Okay, and since we use the local decoding, if the adversary or the prover was trying to cheat, then we could basically detect that with high probability. So we will assume that once the first test is done, f is linear and G is linear. Okay, so in this, if the prover tries to cheat, we will catch them. So once we have done the first test, this is something that we can assume. Okay, and now assume that whatever is a string that f encodes, that doesn't that string, if you take the tensor with itself, that string is not encoded by G. Will this happen? Now, if that is the case, then what we will have is the string that is encoded by G. Okay, so G is the Walsh-Hadamard encoding of some particular string. Let me call it as W. Okay, because it's linear, it is the encoding of some particular string. So let's say G is equal to W. Walsh-Hadamard encoding of W, and is not equal to Walsh-Hadamard encoding of U tensor U. So U tensor U is some string of length n square. Its encoding is going to be some string WH of, it's a string of size 2 raised to n square. Okay, and so this W is not equal to U tensor U. That's the situation that we are. We want to see if we can detect that. Okay. So look at G R tensor R prime. We were querying it at some random location. Now G tensor R prime will essentially be equal to W product with R tensor R prime. So if you write this in the expanded form, this would be equal to summation I comma j wij. Okay, ij will take n different values, so that's going to be n square different entries times r I rj. Okay. The tensor product of R with R prime is going to be some vector of length n square whose ijth entry will be ri rj. Okay, sorry, ri r prime j. So this is the product of G R prime. We can do this because G is a linear function. Any linear function is a Walsh-Hadamard code word, and Walsh-Hadamard code word is produced by taking products of this kind. Okay, and this is nothing but, you can write this in matrix form as vector R multiplied by W multiplied by R prime. Writing it this way, thinking of this as R transpose. Okay, so that's a 1 cross n matrix into an n cross n matrix into a n cross 1 matrix. Okay. So we can think of this in the following way. If you look at Fr times Fr prime, F being a linear code, that's going to be equal to U, and for some particular U, it's going to be U times R, and this multiplied with U times R prime. Okay, and this is equal to summation Ui Ri, I going from 1 to n, and j going from again 1 to n, Ui Rj prime. This by rearranging terms is nothing but summation over all possible values of ij Ri ui uj times Rj prime. And in matrix form, this can be written as again R U or R transpose U R prime, where U is now a matrix which is the tensor product of U with itself. Okay. So what we are assuming is that this W is not equal to U. Okay. If W is not equal to U, we want to say that this test will detect it with high probability. Okay. So if R W R prime is not equal to R U R prime, then our verifier would have rejected. We want to look at the probability of this happening. Okay. So again here, what will come handy is the random subsum principle. So W is not equal to U. You take any word, random word R, W is not going to be equal to RU with probability equal to half. Okay. So U is the tensor product of small u with itself, and W is some other string of length n square. Okay. So since these things are different strings, if W is not equal to U, then RW is not equal to RU with probability half. And for each of those R, so look at any particular R chosen randomly, there is a half probability of that when multiplied with U and W yields different string. For each of those strings, RW R prime is going to be not equal to RU R prime with probability equal to half. Okay. So total for any arbitrary choice of R and R prime, there is a 1/4 probability that RU R prime or R transpose U R prime is not equal to R transpose W R prime. Okay. So basically what that means is compute Fr times Fr prime and GR tensor R prime for some random values R and R prime. If the functions were not proper, if the verifier was, the prover was trying to cheat, then these are going to, this product is going to be different from G R tensor R prime with probability greater than or equal to 1/4. So there is a 1/4 probability that the verifier rejects the incorrect proof. Okay, here incorrect would mean the string G is not a proper encoding of the string that F encodes. Okay, so that happens with probability 1/4. You can try it for 10 different trials. There's only a 3/4 chance of acceptance. So if you try it 10 times, then the chance of acceptance is as low as 3/4 raised to 10. Okay, and that's something like less than a 0.1% chance. Okay, so we can, so now if first step and the second step comes through, that means whatever is being given as the proof, its first part is a linear function, second part is also a linear function, and the first part encodes a particular string and the second part encodes the tensor product of that string with itself, the encoding being the Walsh-Hadamard encoding of those strings. Okay. The third check that we will do is this string U is indeed a satisfying assignment. Okay, this is easy to check if we were allowed to query a lot of positions. Okay, we could look at the entire string U, and from the function F, if we were allowed to query n locations, we can extract the assignment, plug it inside our quadratic equation system, and see if it is satisfied or not. But that is too many queries, because the number of queries is now proportional to the number of variables, but we want to have constantly many queries. One way to check this would be to extract the satisfying assignment or the assignment from F and check the formula, check the system of quadratic equations. But that involves too many queries. We want to do only constantly many queries. If the assignment had n variables, if you extract all the n variables, that would require something like 2n queries. And it is dependent on the number of variables in the equation. But we don't want it to depend on that. So what we will do is we will look at the equations. Suppose there are m equations. We will extract a random subset. And add the equations mod 2. Okay, and then you will get a new equation, and we will check if that equation, that's just one equation, okay, if that one particular equation is satisfied or not. Okay. Suppose you use an assignment which didn't satisfy even one particular equation. So you did not satisfy one equation. Okay. Then when you extract it and submit this particular way, there is a half probability that will be detected, that the random equation that you have made will be unsatisfiable. This random equation is formed by selecting a random subset. If U was not a satisfying assignment to the original system of equation, then the new equation will be unsatisfiable with probability at least half. Okay. But this random equation, let us say that is obtained by choosing a particular subset, let's say a1 x1 plus a2 x2 plus a n square x n square. Okay, because each of the variables here is a term of the form ui uj. Okay, and this should be equal to some particular number. Okay, but this is nothing but, if you look at this vector, all the ai's are some element of 0, 1. Okay, so if you look at the vector, the n square long vector with these entries and call it as z, okay, your gz is precisely this particular sum. Okay, so this sum is nothing but gz. Where z is a vector obtained by looking at these individual ai's. Okay, so you can query at gz location, and if gz is equal to whatever was the sum of these equations, okay, if gz is equal to, let us say, c, when you add them up, you will get some particular value that is equal, then you will say that you is satisfying assignment, otherwise it is an unsatisfying assignment. So by just doing one query, you can check whether U is a satisfying assignment. If U was indeed satisfying assignment, the query would tell yes, it is a satisfying assignment. If it is not a satisfying assignment, there is at least a probability half of finding that this is not a satisfying assignment. You can repeat it 5 times, and the probability of success becomes 1 minus 1 by 2 to the power 5. Okay. So these 3 tests ensures that the function f and g are linear, and g encodes the tensor product of whatever f encodes, and whatever f encodes is a satisfying assignment. Once these 3 are checked, we know that quad EQ is satisfiable. Okay. So what we've argued is any instance of quad EQ can be converted into a proof string pi, and in pi we can just query constantly many locations, and constantly many queries requires only poly n number of random bits. Okay. So that brings us to the end of the proof of weak PCP theorem.